Okay, this is not a simple pendulum, but it behaves in a way very similar to a simple pendulum. It'll oscillate. Now, of course, I'm holding it with my fingers kind of lightly, but I've got to keep nudging it a little bit to keep it oscillating because there's a friction loss where my fingers hold it. Okay, well, we're going to pretend that this thing is swinging freely with no friction. Okay, so I'm going to simulate that with my fingers a little bit. So there it is swinging. Now let's go ahead and let it stop. Now, there's a magnet here, and this magnet repels this magnet, so I can deliver an impulse to this thing. And it eventually comes to rest. If I want to compensate for the friction, I can do this. There we are. Okay. Now, if I time this impulse pretty carefully, I can pretty much make this thing stop. Okay, and then I can get it going again, and I can keep reinforcing it when it gets to the extreme position on this side. Okay. Or I can keep reinforcing it when it gets to the extreme position on the other side. Well, there are various ways I can reinforce this pendulum, and we'll refer to those when we do this model. Now, just a little background, the physics of the situation, because most people in this course have had the physics, you can easily understand how the equation arises. If we haven't already seen this earlier in the course, and generally we probably would have. Okay, so we know that net force equals mass times acceleration. Now, to model this pendulum, we really do it with net torque equal to moment of inertia times angular acceleration. But we're going to pretend we have a simple pendulum. The models are identical. Okay, so acceleration is a second derivative of position. So if x is your position function, and acceleration is a function of time, x is regarded as a function of time, derivatives are with respect to time, then your net force would equal mass times x double prime. Well, your net force on a simple pendulum arises from the fact that you have gravity acting downward on the pendulum, tension acting to support the pendulum, tension acting to shorten the string or wire, whatever it is from which the pendulum is suspended. So the tension pulls in on both ends. The tension that applies to the mass at the end of the pendulum is, of course, the tension from this end, tending to pull the string shorter. Okay, so we have this. Now, for small oscillations, or small displacements from the equilibrium position, which would have been a better way to state that, tension's pretty close to mg. And the closer you get to equilibrium, the closer it is. So we neglect the difference. If tension is approximately equal to mg, then the tension has components well, it has a component in this direction. So we'll call this a tension T sub x, the tension in the x direction. And here's your tension. Of course, these are vectors. And this can be represented as a vector or the scalar amount of the vector. Okay, this tension tends to pull the mass back toward equilibrium. For small angles, the vertical component of the tension is going to be equal to mg. Well, the vertical component of the tension, well, no, because the motion is in a circular direction. So we're going to neglect all that, but the simplest model has an x component of the tension here that turns out to be equal to mg over L times x, badly drawn picture here, where x is your displacement from equilibrium. Okay, well, that should be familiar to you. This tells us that the net force is then equal to mg over L times x. So we have mg over L times x equals mx double prime. And actually this is negative mg over L times x. Because of course it's in the direction opposite x. If x is in this direction, the mg over x is this, and I'm being a little cavalier with the vector notation, but we're not going to worry about that. Those details can be filled in, but just trying to give you the general idea. Well, this equation becomes x double prime plus g over Lx equals 0. Second order differential equation. Linear second order differential equation. This equation has a familiar solution and so forth. Now the equations that we look at, and often the text that we're using uses y for the variable, for the position. So if it was y, and if you get the same model if you have a mass suspended from a spring, and y is natural for vertical motion. Okay. The general equation would be y double prime not plus y prime plus y equal to 0. Okay, just like this one, except we don't have that g over L here. That's your paradigm equation, and of course you can have any constant you want depending on what g and L are. It's possible for g over L to give you a unit constant, so this is perfectly good. If it don't have a unit constant, of course, then it could be y prime plus any constant times y equals 0, and this describes the motion of the pendulum. Unless you have an extraneous force. So when I apply that impulse, the net force now becomes equal to the impulse. So with an extraneous force, and let's call F the applied force, F net now equals negative mg over L times x, because the string still has a tension, still pulling the thing back, plus whatever your applied force is. And let's put an APP on this force for applied, just a subscript to distinguish it from F net. In this case, of course, then your equation becomes, well, when you carry out the constants and stuff, you're going to get y double prime plus some constant times y equals your applied force. And now you have driven harmonic motion. Okay, so that's the context here. The applied force could be our impulse. And the applied force could be a unit impulse delivered at time t0, so be some multiple at least of delta of t minus t0, your Dirac delta function. Okay, could be a unit impulse delivered at this time, or it could be a multiple of that unit impulse, so that you would end up with an equation of the form, in the simplest form, this, where whatever constitutes a unit impulse in the system of measurements that we're using could be applied by this magnet, could be represented by this magnet. This magnet isn't a perfect impulse. A sharp rap on the thing, we have the thing oscillating and we hit it with our knuckles. Hopefully don't knock the magnet off. Okay, we have that. That's closer to an instantaneous impulse. The impulse of that magnet really is spread over probably a couple tenths of a second if I do this very quickly. And it's not a level impulse. It's more not a Gaussian in that case, but something much like that. Your force would be, force versus time would have a graph that would look something like a bell-shaped curve. Okay, well, enough about that. We could also have the equation where we have drag, and that would be like y double prime minus, say, gamma y prime plus cy equals F applied, and that actually should be plus. Your drag force be over on this side, and it'll be opposite your velocity, so it'd be negative on this side. Bring it over to this side as positive. Okay, well, those are just preliminary ideas, and what we want to look at is what happens when your applied force is an impulse or a series of impulses. We know how to handle the equation, and we've done it much earlier in the course for a variety of possible applied forces using just the standard methods of higher order equations, higher order differential equations, linear differential equations, even nonlinear. The thing that we want to do now is we want to go to impulse forces which need to be handled with Fourier transforms. And that's really where we're at now, and we want to see how these things work out.